Hi students, so welcome you all again for the CET classes. In the previous class, we have studied some of the important topics, that is domain, codomain and range. So we have studied some of the important topics like relations and the examples of relations, domain, codomain, range, functions, representation of functions. Okay, so algebraic method of solving functions also we have seen in the previous class. No problem. The important one was this thing, that is rules for finding the domain of a function. Clear? So this we were discussing in the last class. In that first we have studied about algebraic functions. And whenever you are finding the domain of a function in the algebraic, the denominator should be non-zero. This we have already studied. And second point is expression under the even root should be non-negative. This also we have studied clearly in the previous class. If you have any doubt, you can watch my previous video. Clear? Next, about trigonometric functions also we were studied in detail. We have seen sin x and cos x and the graph of sin x and cos x in the previous class, and where sin x and cos x are defined and what are its domain and range, that we have studied in the previous class. We have also studied tan x and sec x, where it has been defined and where it is not defined. That also we have studied. This is the point where our tan x is not defined. This is the point where tan x is not defined, and we have gone through this cot x and cosec x are defined for all real values of x except at n equal to pi. And this was our homework in the previous class. I think you have all done this homework. So now I will move to the next concept, that is inverse trigonometric functions. Clear students? So here inverse trigonometric functions means first you must know what is inverse function. If you know what is inverse function, then you can understand what is inverse trigonometric function. Clear? So for that reason, first we shall see in detail about inverse function. Inverse function means, for that let us consider, let let f be a function from a to b. Let f be a function from a to b. Here a is domain, b is codomain. A is domain, B is codomain. First we have to understand this particular terms if you want to understand the inverse function. Okay. So what we do whenever we define a function f of x equal to y, x will be in the domain, y will be in the codomain. Clear? So by defining the function, as you give the inputs to x, you are going to have outputs in y. So from this you can define 1 1, onto many one, like this, so many kind of functions. Okay, I will take only these three because of our simplifications, and in these three I will define only these two functions, because these two functions are very important for us to define inverse function. Why means, if you want to define inverse function, the f if you want to define the inverse function, the function must be 1 1 1 1 and onto. The function must be 1 1 and onto. Here what is 1 1 and what is onto, that is very important. Okay, so for that I will define first 1 1 function. If you know what is 1 1 function, then it will be very much clear to define onto function. 1 1 function means this is your domain, this is your codomain. I have some elements here and also I have some elements in this set. Okay. Now what I will do, I will map first element to the second element to first element, third element to third element, fourth element to fourth element. Okay, that means every element of domain, see this, every element of domain of domain are having are having unique image are having unique image. What is the meaning of unique image? If you see here, see this element, it has only one image. See the second element, it also has only one image. See the third element, it is also having the only one image, and the fourth element is also having one image. Clear? So that means all are having unique images. Suppose if you want to know in the clear picture what is unique and what is non-unique, if you have like this some elements here, first element maps to first element, second element maps to second element, and third element maps to the second element. If this happens, here the second element and the first element are having the same image. The second element and the third element are having the same image. Because of this, we say it is not unique. Because of this, say it is not unique. Clear? So, this is what we have to understand. Okay. After this, suppose, see, if you want to write it in the mathematical form, if you want to write it in a mathematical form, how you are going to write? We write it as, if f of x1 is equal to f of x2, if f of x1 is equal to f of x2, this must imply that x1 is equal to x2. This must imply that x1 is equal to x2. How you are going to understand this in clear? If we take one example, it will be very simple. So for that, let us take one example and let us try to solve it. No problem. But before going to the example, please make sure that 1 1 function means every element of the domain must have the unique images like this. If it is having, if two elements are having the same image, then it is not unique. That has to be clear. And the definition of 1 1 function is written as, if the function f of x1 is equal to f of x2, it implies x1 is equal to x2. This also you must understand. Clear? So now let us see one of the example for this. F of x1 is equal to f of x2. You have to show that x1 is equal to x2. This you must remember. If you remember this, everything will be very simple. For that I will take f from natural numbers to natural numbers. Function is f from natural numbers to natural numbers, defined as f of x equal to x. Defined as f of x equal to x. So here if the function f of x equal to x is defined, if the function f of x equal to x is defined, then let us see how it is going to be 1 1. Here the domain is natural number set, codomain is also natural number set. From that you can see 1, 2, 3, 4, 5. Here also 1, 2, 3, 4, 5. If I put f of 1 for x value, output is also what? The same term x, so it will be 1. If I take f of 2, output will be what? 2. If I take f of 3, output will be what? 3, because the input which you are giving, the same output you are getting. So for that reason, if I take f of 4, output will be 4. If I take f of 5, output will be 5. Here this is all things are your rough work. Here this thing is your rough work, just to understand. Okay. So now you can see that 1 maps to 1, 2 maps to 2, 3 maps to 3, 4 maps to 4, 5 maps to 5. All the elements are having the different and unique images. Okay. So if this happens, already we have seen this is called unique image, and if this is unique image, then it is going to be called as 1 1. But how to write this? See, here this is also rough work. This is the rough work which we have understood. But whenever you are solving this, if it is 1 1, you have to show that f of x1 equal to f of x2 for every x1 comma, or you can write it as for every x belongs to n. For every x belongs to n, it implies x1 is equal to x2. This you have to write if we ask in exam, or if someone asks what is 1 1, if this given function is 1 1 or not, what you have to write, this thing you have to write and you have to explain, but this thing you have to understand. Okay, when you are representing, you have to represent like this, but before representing this, these two things are very important to do in rough. Clear? If this rough work is done, then you can write this. Okay. So then how to show it is not 1 1? That is also very important. So for that I will go for the same example. But what I will do, I will take f from integers to integers. This is an integer set. Okay. Again f of x is defined as x square. Here f of x is defined as x square. Previously I was defined f of x is equal to x from n to n. But here I am defining f of x equal to x square. From this I am going to understand. So if I put f of 1, you are going to get 1 square. So this is 1. If I put f of minus 1 minus 1 square, again you are going to get 1. See here, what happens? F of 1 is equal to f of minus 1. F of 1 is 1, f of minus 1 is also 1. Are you getting my point? Because x value is 1, here x value is minus 1. If I simplify, 1 square will be 1, minus 1 square will be also 1. From this what you understand, f of 1 is equal to f of minus 1. But what we know, 1 is not equal to minus 1. 1 is not equal to minus 1. So hence we can say that it is not 1 1. Hence we can say that it is not one function. It is not one function. Clear? So for that, if you draw a Venn diagram, see this 1, minus 1, 1, 2. 1 maps to 1, minus 1 maps to 1. Here 1 and minus 1 are having the same images, therefore it is not 1. Therefore it is not 1. Clear? So if I prove this, it is not 1, then here you have to write this example. If someone asks in exam or anywhere, you have to write this example. But in CET exams, no problem, you can directly simplify and directly you can go for the MCQ type questions. But whenever if they ask in theory exams, you have to write this example in your exam paper. It is not as same as your 1 function. If it is 1, then you have to write definition. If it is not 1, then you have to write example. Please remember this. Clear? Okay. So from this we understand that for a function to be in a 1, what must be there, and for the function not to be in a 1, what it has to satisfy. From all these things, what we understand? We understand what is 1 function. Okay. Now let us go for onto function. Now let us go for onto function and let us understand what is this onto function. Again, let f be a function from a to b and defined by f of x equal to y. So for onto for every y belongs to b, that is codomain, for every y belongs to b, that is codomain, there must exist an x belongs to a. There must exist an x belongs to a. Then it is called onto. Then it is called onto. Clear? So what is meaning of this? That is also very, very important. See, this is domain, this is codomain. What they are saying, for every y belongs to b, for every y belongs to b, 1, 2, 3, 4, 5. Here I will write some these elements. Okay. For every element of y belongs to b, there must exist x belongs to a. I will map this to 1, this for also 1, this to 2, and this for 3. Clear? And I will take one more example. Here again I will have only 3 elements. So first one maps to 1, here this maps to 2, here this maps to 2, here this maps to 3. From all this, what we understand? From all this, what we understand here? We understand that here there are some. Okay, students. So what happens here? We have 4 and 5. We have 4 and 5 which are not having any pre-images, or any element of domain is not having 4 and 5 as image. That means 4 and 5 are not an images of any elements of domain. But here every element of the domain is having pre-image. See this. Here 4 and 5 are not having pre-images. Every element of the domain are having pre-images. That means for every y belongs to b in the codomain, there exists x belongs to a. Here 4 and 5 are the two elements for which there are no elements in the domain. That's why what happens? This becomes not onto. This becomes onto. Clear? So like this we define 1 and onto. After defining this 1 1 and onto, now we move for inverse function. Now we move for inverse function. You can take the examples of onto in your NCERT textbook and you can see, so that you will be very much clear. Are you getting my point? Okay. So now I will move for inverse function. Now I will move for this inverse function. What is inverse function? Again same, let f be a function from a to b. Now f inverse means this is a function from b to a. Clear? Here domain is a, codomain is b. Here domain is b, codomain is a. So if inverse exists, if inverse exists, domain and codomains codomains are interchanged or interchanged. Clear? So to interchange this domain and codomain, the f has to satisfy both 1 1 and onto, both 1 1 and onto. Clear? So if it satisfies both 1 1 and onto, we call this together as bijective function. We call this together as bijective function and we say inverse exist. We say inverse exist and we can write it as f inverse from b to a. F inverse from b to a. So to exist inverse function, the very important thing is it has to be both 1 1 and onto. It has to be both 1 1 and onto. Then we say that this particular function is what? Bijective. So this together is called as bijective. If the function is bijective, then inverse is going to exist. Hence, we can define the inverse function from b to a. So this is what your inverse function. So from this all basics, now we shall move to your inverse trigonometric functions to find the domain and codomain of inverse trigonometric functions. Clear, students? Okay, students. So now here let us see that in the inverse trigonometric functions, the first one is sine inverse x and cos inverse x are defined for -1 to +1. That means here they are taking sine inverse x and cos inverse x. So they are telling that these two functions are defined for -1 to +1. That means this is your range. This is your range. Then what is domain? Then what is domain? That is very important. Clear? Because this is defined for -1 to +1 means, sorry, here this is your, okay students. So here first let us see sine inverse x and cos inverse x. They are telling that sine inverse x and cos inverse x are defined for -1 to +1. That means sine inverse x and cos inverse x are defined for minus 1 to plus 1. That means they are defined in the interval of minus 1 to plus 1. That is closed interval minus 1 to plus 1. Clear? So, if it is defined from minus 1 to plus 1, this is called as domain. This is called as domain. Then what is range? That is also very, very important. In this domain, what is the range? For that, let us go through the graph of sine inverse x and cos inverse x. So, this is sine inverse x and this is your cos inverse x. Clear? See here, this is the interval that is from minus 1 to plus 1. It is defined from minus 1 to plus 1. You can see this. So from minus 1 to plus 1, this is going to be the graph of sine inverse x. So from this graph, what we understand, it is defined in between pi by 2 to minus pi by 2. Pi by 2 to minus pi by 2. So in this particular term, we can say that it is defined. That means sin inverse x is defined for x is greater than or equal to minus 1, lesser than or equal to plus 1. This is the domain and range is going to be minus pi by 2 to plus pi by 2. Minus pi by 2 to plus pi by 2. Clear? So, sine inverse x is defined from closed interval minus pi by 2 to, sorry, sine inverse x is defined from minus 1 to plus 1 to minus pi by 2 to plus pi by 2. This is going to be the domain and this is going to be the range. Clear? Why they are restricting this domain? Because only in this interval, sine inverse function is both 1 1 and onto. Both 1 1 and onto. Clear? On the same way, you can see here also, see this, minus 1 to plus 1. So in this graph, you can see about cos inverse x. You can see about cos inverse x. This is the where our cos inverse function is both 1 1 and onto. Both 1 1 and onto. Here cos inverse x is defined from minus 1 to plus 1 goes to 0 to pi. So this is domain and this is range. Clear? But for the sine inverse x, minus 1 to plus 1 minus pi by 2 to plus pi by 2. See this. Here it is minus pi by 2 to plus pi by 2. Here this is 0 to pi. This is very, very important. Clear? The range of sine inverse x is minus 1 pi by 2 to plus pi by 2. Cos inverse x is 0 to pi. Are you getting my points? Clear? So like this, we are going to define the sine inverse x and cos inverse x in the required domain, that is -1 to +1, and here also -1 to +1. Clear? Okay, students. So now let us move to the previous slide and let us see the next one, that is tan inverse x and cot inverse x. So in the function tan inverse x and the cot inverse x, tan inverse x and the cot inverse x are defined for all real values of x. That means defined for all real values. What is meaning of all real values? This is real number set. This is real number set. That means tan inverse x and cot inverse x are defined defined for your real number set. That means domain is real number set. Clear? Now again let us go for the graphs and let us understand the domain and codomain of tan inverse x. Clear? So see this graph, students. This is the graph of tan inverse x. This is the graph of tan inverse x. You can see that from minus infinity to plus infinity on the x axis, you are having your graph. You are having your graph. Clear? That means for all real values, for all real values, it is defined. For all real values, it is defined. If you see, in the tan x, it is not defined for pi by 2. Clear? It is not defined for pi by 2. But here you can see that in the tan inverse x, it is defined for all the real values. It is defined for all the real values. Then what is range? That is very, very important. What is range? Clear? So the range of tan inverse x, the range of tan inverse x, you can say it is from this particular point on y-axis to here. That is nothing but from minus pi by 2 to plus pi by 2. Minus pi by 2 to plus pi by 2. See here. One of those curves limiting range of tan inverse x to minus pi by 2 to plus pi by 2. Clear? So you can see that tan inverse x is defined from minus pi by 2 to plus pi by 2. Defined means that is the range. Clear? It is defined for all the real values and the range will be minus pi by 2 to plus pi by 2. Clear, students? So on the same way, you go through the cot inverse x and you can see where it is defined and where it is not defined. It is also defined for all real values as we previously said. It is also defined for all real values. All real values. Then what is range? See here, you can see from 0 to 1. You can see from 0 to, sorry, that is 0 to pi. This will be the range, that is 0 to pi. Clear, students? So this is a simple understanding of tan inverse and cot inverse x, because cot inverse and tan inverse are defined for all real numbers, but the range is very, very important. Range for the tan inverse x is minus pi by 2 to plus pi by 2. For this it is minus pi by 2 to plus pi by 2, and here it is 0 to pi. Here it is 0 to pi. Clear? So from this we understand tan inverse and cot inverse are defined in these intervals just because of to be bijective. To be bijective. If it is bijective, then we say it is defined for inverse. Then we say it is defined for inverse. Because of this particular things, what we can say, tan inverse and cot inverse are restricted in the intervals. Restricted in the intervals, but the domain is what? Domain is real number set, that is R. For the tan inverse x, the range is minus pi by 2 to plus pi by 2, and for the cot inverse x is 0 to pi. So please remember all these particular terms. If you remember all these particular terms, then it is going to be very, very easy. Clear, students? Okay. So now let us move forward with sec inverse x and cosec inverse x. So I will give this as an homework to you all. So see, the domain is minus x is lesser than or equal to minus 1, x is greater than or equal to plus 1. Are you getting my point? That means minus infinity to minus 1 and plus 1 to positive infinity. Here the sec inverse x and cosec inverse x are defined. So from this I have already given in the slide what is domain. Now your task is finding range. Now your task is to find range. Clear? So try to find the range of sec inverse x and cosec inverse x. Are you clear? Okay, students. Now let us continue with logarithmic function. Okay. So we have already seen sin inverse x, cos inverse x, tan inverse x, cot inverse x, sec inverse x, and cosec inverse x. Now let us move for the logarithmic function. Clear? So what is log function? Log function is defined as f of x equal to log x. This is a natural log function. Natural log function. But usually we write it in the form of log of a to the base b. B is called base and a is called indices. Clear? So here, here what happens? Log function is defined whenever this term is greater than 0 and whenever b is not equal to 1. Whenever b is not equal to 1, that means b is also greater than 0. B is also greater than 0, but b is not equal to 1. Clear? So it is defined for all the terms whenever b is greater than equal to 0, but it has to be not equal to 1. Leaving this a single point, it is defined for all the terms. It is defined for all the terms, and a must be always greater than or equal to 0. See this, log a to the base b. The condition for a is always greater than 0. Condition for b is b greater than 0 but not equal to 1. B greater than 0, but it has to be not equal to 1. I think if I explain this particular thing with the graph of log function, it will be very much clear. See here, f of x is equal to log x to the base b. F of x is equal to log x to the base b. Usually we were talking about log a to the base b. In the place of x, we have taken a. Okay. So here what they are saying, b must be greater than 1. B must be greater than 1. See here. This is b comma 1 log b to the base x, and the output of log are taken like this. So this will be the nature of log function from from 0 to positive infinity. This is 0 to positive infinity on x-axis. They are taking only for the positive real numbers. So for positive real numbers, the graph is defined from where 0 to, see, it is defined from 0 to positive infinity whenever b is greater than 1. That is base must be always greater than 1. If the base is in between 0 to 1, if the base is in between 0 to 1, the graph changes its nature. The graph changes its nature. It will be again from 0 to positive infinity, but it will be from here on y-axis it is positive infinity. Here it goes towards like this. Okay. So this is the nature of log whenever b is in between 0 to 1. This is whenever b is greater than 1. From this we understand the nature of the graph is like this. And another nature of the graph is like this. Clear? So these two are the nature of graphs. Nature of graph whenever b is greater than 1. Here whenever b is in between 0 to 1. Very important thing is, here your base should be in between 0 to 1. Here base should be greater than 1 to have the nature of graphs like this. Are you getting my point? So by knowing this, you have to understand one more point, that is, if I write a to the power of b is equal to some x, now if I take okay students, so with this log property, let us understand one more very important point, that is a to the power of b equal to x. If you have a to the power of b equal to x, this can be written as b is equal to log x to the base a. Very important. See this. Here the base is a, indices is b, or you can say base is a, power is b, that is equal to x. That means if I have a to the power of b is equal to x, now if I want to find this b, for suppose, let us say a to the power of uh, a to the power of something, a to the power of 3 is equal to x. Let us consider this. Okay. Or you can write 3 to the power of 3 is equal to 27. No problem. Clear? I don't know this. I have only knew 3 to the power of b is equal to x. 3 to the power of b is equal to x. Now I want to find, or you have here 27. No problem. 3 to the power of b is equal to 27. It's a very simple problem. No worries. But I'm just taking a simple example. How to simplify log. Now if you want to find b, you can write b is equal to log 27 to the base 3. Log 27 to the base 3. If you see this in log book, you are going to get the answer of B. Clear? Already you know how to see the logbook, that all things, but again I am telling that if you want to understand this particular function, this or this particular graphs, with this graphs, this knowledge is very very important. That is, if we are writing if we are writing a to the power of b is equal to x, I can simplify this as b is equal to log x to the base a. Please remember this. Suppose you have log x to the base a, this can be written as log x to the base a equal to b. This can be written as x is equal to a to the power of b. In both the cases you can write. If you have this, you can write this. If you have this, you can write this particular term. Clear? So this will be very very useful in the coming classes. So please understand this. So it will be very helpful. So these two are the nature of the graphs. You have to understand that whenever base is greater than 1, nature will be like this. Whenever base is in between 0 to 1, the nature of graph will be of the second kind. Okay. So already we know that if the base and a are the greater than 0, then only the log function is defined. Clear? Okay. So now from exponential function, already with the log function we have seen the exponential function where a is greater than 0, it is defined. That is, if a to the power of x has to be defined, a has to be greater than 0. This is very very simple problem. No worries. Clear? So from that, please understand the relation between log and exponential function. Log and exponential function. If you understand the relation between log and exponential function, then it is very very useful for your coming classes. Okay. The relation between log and exponential function is very simple. See, if I have a to the power of x is equal to b, I can write x is equal to log b to the base a. This is nothing but the relation between exponential function and logarithmic function. Exponential function and logarithmic function. Clear? So before coming to the next class or next CET, you go through what is the relation between these two in some more topics and understand it. Okay. And you can also see the nature of graph of exponential function also. That is like this. So try to see this. It is an exponential function. Okay. This is log function already, which we have seen. So in thoroughly you can go through the exponential function also, and you can see the nature of graph. Clear, students? Okay. Okay, students. So before I wind up this class, let us go through these simple properties of log and exponential, because these things are going to be very useful in your coming classes. So let us do these things in this class, and in the next class I will continue with the next topics. Okay. So here, while doing multiplication, this is laws of exponents. Laws of exponents means, see, suppose you have 2 to the power of 3 into 2 to the power of 5. I can write it as 2 to the power of 8. The only condition is the base term has to be same. That is what they have written here. X to the power of m, x to the power of n, both are multiplied. So x to the power of m plus n. That means the power are added. Clear? Whenever there is a multiplication with this kind of terms, you can also write 5 to the power of 2 multiplied with 5 to the power of 3 as 5 to the power of 5. That is nothing but 5 to the power of 2 plus 3. Clear? The base terms has to be same to do this simple logic. Suppose if you are dividing x to the power of m and x to the power of n. Clear? So x to the power of m is divided by x to the power of n. This can be written as x to the power of m minus n. That means 2 to the power of 5 divided by 2 to the power of 2 can be written as 2 to the power of 5 minus 2. Clear? If you want to see, you can see this by calculating. This will be 32 divided by 4, so that will be 16. Here also you can see 2 to the power of how much you are going to, okay, here you are not 16, this is 8. Here you can see this is 2 to the power of 3. If you simplify 2 to the power of 3, you are going to have 8. Okay. So please remember this, that is x to the power of m multiplied with x to the power of n can be written as x to the power of m plus n. X to the power of n divided by x to the power of n can be written as x to the power of m minus n. So exponential form also can be written as x to the power of m to the power of n is can be written as x to the power of mn. That means 2 to the power of 3 whole to the power of 5 can be written as 2 to the power of 15. 2 to the power of 15. You have to multiply these two terms. Clear? Anyways, x to the power of 0 is 1. Please remember this 0 property, that is x to the power of 0 is 1 and x to the power of minus 1 is 1 by x, that is inverse. 2 to the power of minus 1 can be written as 1 by 2. 3 to the power of minus 1 can be written as 1 by 3. 5 to the power of minus 1 can be written as 1 by 5. These are called as inverse, and anything to the power of 0. 2 to the power of 0 is also 1. 3 to the power of 0 is also 1. 4 to the power of 0 is also 1, like this. Clear? So x to the power of 0 is 1. So my dear students, this is multiplication law, division law, exponential law, zeroth law, and this is inverse law. Very, very important terms. It is going to be very, very useful. So please understand this particular terms. Clear? That is x to the power of m into x to the power of n can be written as x to the power of m plus n. X to the power of m divided by x to the power of n can be written as x to the power of m minus n. X to the power of m whole to the power of n can be written as x to the power of m into n. X to the power of 0 is written as 1. X to the power of minus 1 is written as 1 by x. Clear? These all terms are your laws of exponents. Your laws of exponents. Clear? On the same way, now let us go for the laws of logarithm or the laws of log function. Clear? For the multiplication, if I write log of, see here, log of a into b, this can be written as log a plus log b. See this, the log property for the multiplication tells that if you have log of a into b, that is nothing but log of something like this, that is 2 into 1 by 2 or 1 by 3. Let us don't take this. Let us take log of some term 2 into 3. So this can be written as log of 2 plus log of 3. Are you getting my point? You can also solve log of 6, no problem. Clear? Log of 6 will be equal to log of 2 plus log of 3 only. Are you getting my point? Because 6 can be written as 2 into 3. So now by using the log properties, you can write it as log of 2 plus log of 3. On the same way, log of 20 can be written as log of 5 into 4, that is nothing but log of 5 plus log of 4. Clear? So this is called multiplication law. See this, it is called multiplication law. On the same way, division law, log of a by b, that is log a minus log b. That is nothing but log of 2 by 3 can be written as log of 2 minus log of 3. Clear? On the same way, say this. If you have log of 2 to the power of 3, you can write it as 3 times of log 2. 3 times of log 2. That is exponential rule. exponential rule of log. Okay, that is nothing but log of 10 to the power of 2 can be written as 2 into log 10, 2 into log 10. Clear? On the same way, please remember this, log 1 is 0. Please remember this, log 1 is 0. On the same way, x to the power of 0 is 1. As I previously discussed, 0 will be equal to uh, log 1 to the base x, log 1 to the base x. Here x value will be e, that's next thing, but please remember that log 1 is going to be 0. Log 1 is going to be 0 with the natural log, 0 with the natural log. Clear? On the same way, log of x to the power of minus 1, this first can be written as log of 1 by x, or this also can be written as minus log x. No problem. Minus log x is also equal to log of 1 by x. See here, log x to the power of minus 1 can be written as log of 1 by x. By using this rule, x to the power of 1 can be written as 1 by x. Also this can be written as minus log x. Also this can be written as minus log x, because apply the properties here. Apply the properties here. What you are going to write? Log 1 minus log x. See this rule. A by b rule apply here. You have to apply a by b, log of a by b rule to log of x to the power of minus 1. So if I apply this log of a by b rule to the log of x to the power of minus 1, so log 1 minus log x, log 1 is already 0, remaining term will be log x. Clear, students? So please remember these all terms which I have discussed here. These things are very important. Clear? So please make sure that these all terms are going to be very easy before you come to the next class.